A few years ago, I made a video looking at the idea of gravity energy storage. Now, if you remember that one, it focused in particular on a Scottish company called Gravitricity, who were developing a system that involved lowering and raising massive weights inside disused mine shafts. At the time, it seemed like a very elegant solution. Use gravity, use existing infrastructure, keep things relatively simple. What could possibly go wrong? Well, quite a lot as it turns out, because since then, Gravitricity has quietly slipped out of the picture, entering voluntary liquidation with barely any assets left to distribute. And that, my friends, is often the moment when an idea moves from promising concept into the much harsher environment of real-world engineering and economics. But here's the interesting thing. At almost the same time that Gravitricity has fallen away, a whole new wave of research has emerged suggesting that maybe the core idea wasn't wrong at all. So are we having another crack at utilising old mine shafts then? Because considering there are literally millions of them strewn all over the landscapes of our planet, it really would be very helpful if we could. Hello, and welcome to Just Have a Think. Gravity storage has its appeal, doesn't it? Those of you with long memories may also recall me talking about another Swiss-based company called Energy Vault. They were even more ambitious than Gravitricity. They were going to build massive towers all over the world and hang a bunch of 35-ton weights off them, all of which could be raised and lowered on demand. The obvious drawback of potential energy moving towards zero the lower down the tower a block was positioned did not go unnoticed by the company's critics. Nor did the ever so slightly concerning propensity for those massive weights to start swinging violently when the wind picked up a bit. Anyway, Energy Vault's second iteration was housed inside a massive warehouse-style building, and it does appear they did actually manage to sell one of these things to China, who, let's face it, will literally try anything when it comes to energy storage, won't they? Other than that, though, things have gone a bit quiet at Energy Vault, so while I thought I should at least mention them for completeness, I think I'm going to leave them aside for the purposes of the rest of this video. The renewed interest in mine shaft gravity storage that I mentioned earlier actually comes from Oak Ridge National Laboratory over in the United States. Before we get stuck into all that though, I'm very much hoping you might just take the trouble to click the free like and subscribe buttons just down here. I'm a one-man band here at Just Have a Think, and grabbing the attention of the mighty YouTube algorithm is becoming increasingly difficult every week as more and more AI clickbait floods the platform. So if you want to keep up with my latest videos and you feel you could support the channel with those little clicks, you really would be helping me enormously. So what are the folks at Oak Ridge telling us then? Well, they're suggesting that abandoned coal mines really could still play a very significant role in the future of energy storage, just not necessarily in the way we originally imagined it to be. The key shift is that instead of focusing purely on lifting and dropping heavy weights, the Oak Ridge team is increasingly looking at using mines as underground reservoirs for storing energy in other forms. Broadly speaking, there now appear to be three main approaches for exploration: gravity systems, a bit like the Gravitricity model, a version of pumped hydro systems, essentially creating underground water batteries, and the more traditional compressed air systems that have been attempted many times in one form or another for well over a century. By the way, it's worth noting that disused coal mines can also potentially be repurposed as low-carbon geothermal heat sources by pumping relatively stable warm water to the surface and passing it through heat exchangers and heat pumps to provide heating for nearby homes, offices and industrial buildings. That's a slightly different approach that we may look at in a future video, but it's a bit outside the scope of this one. Let's start with the strongest contender, which appears to be pumped hydro. If you've been watching this channel for a while, you'll know that pumped hydro is not exactly a new idea. We've been using it for well over a century. Very simple concept: pump water uphill when electricity is cheap or abundant, and then let it flow back down again via turbines and generators when electricity is needed. Straightforward, reliable and proven. In fact, pumped hydro already accounts for the vast majority of global grid-scale energy storage. So the question researchers are now asking is, can we replicate that system underground using abandoned mines? According to recent studies, including work from Oak Ridge, the answer appears to be yes, in principle. Mines already give you vertical shafts, large underground voids, and crucially, in many cases, existing grid connections. So the theory goes Instead of building huge dams and reservoirs on the surface, maybe we can repurpose what's already there and cut out a whole bunch of costly and time-consuming bureaucracy in the process, all of which makes for a very attractive proposition. But of course, life is never that simple, is it? When you start digging into the research, and I've looked at quite a few research papers on this one, a pattern starts to emerge. The physics is easy, the geology is hard. For example, researchers highlight a number of key challenges, not least of which are water leakage through fractured rock, chemical reactions between mine water and surrounding materials, structural instability in old tunnels and shafts, and complex fluid dynamics in irregular underground spaces. In fact, some studies suggest that the behaviour of water inside these underground systems is fundamentally different from traditional pumped hydro reservoirs. So this isn't just pumped hydro but underground, it's actually a whole new engineering problem. And then there's the issue of site suitability, arguably the biggest constraint of all, because while there are hundreds of thousands of abandoned mines all over the world, only a fraction of them are likely to be completely suitable. Some are flooded, some are unstable, some simply don't have the right geometry, and that leads to the rather frustrating conclusion that subterranean pumped hydro is not the simple, scalable, copy and paste solution that we'd like it to be. It's a site-specific engineering challenge. That's not to say it's impossible, but it certainly comes with a hefty chunk of expectation management. So what about gravity storage then? Another beautifully simple idea, at least on paper anyway. Lift something heavy and then release it later on. This one also has some very attractive properties. You don't get any self-discharge like you do with a chemical battery. You get extremely long operational lifetimes and potentially comparatively low operating costs. In fact, one academic paper estimated global storage potential from mine-based gravity systems in the range of 7 to 70 terawatt hours, which is not trivial. The trouble is there's still very little real-world validation, and the collapse of gravitricity, despite a technically sound concept, suggests that getting from demonstration to commercial deployment is extremely difficult, not necessarily because the idea doesn't work, but because the economics, logistics and engineering complexity start to stack up very quickly. It's the dreaded valley of death that we've talked about so many times on this channel over the years. Okay, well what about good old compressed air then? This one turns out to be a bit more controversial, and in fact just recently my YouTube buddy Rosie put out a very detailed video looking specifically at the pros and cons of this technology, which I've linked in the description and which is well worth a watch. One of the things Rosie does very effectively is place the technology in its historical context. Before electricity became dominant, compressed air was actually seen as a serious contender for transmitting energy over long distances. Entire networks of pneumatic tubes were built in cities like Paris, moving messages and small goods with pressure differentials. But ultimately, electricity won out, largely because it was far more efficient at scale. And that same efficiency challenge still sits right at the heart of compressed air systems today. Apparently, one of the key technical challenges lies in what happens to heat during those processes. Early systems, like the famous Huntorf plant in Germany, used what's called a diabatic cycle, which means the heat generated during compression is lost, and then fossil fuels are burnt to reheat the air during expansion. Completely counterproductive. Modern systems are moving towards a so-called adiabatic design, where the compression heat is captured and reused. And then there's the isothermal approach, the sort of low and slow idea that attempts to maintain a constant temperature throughout the process. According to Rosie, those newer technologies can push efficiencies up from around 40% to potentially 60 to 70%, with some designs aiming even higher. So maybe there's some potential in newer versions of this very old technology. In fact, using huge underground cabins for compressed air energy storage is a much better and much more cost-effective idea than trying to do it above ground in man-made tanks. So developers have been looking for things like salt caverns, hard rock formations, aquifers, and abandoned mines. A Canadian company called Hydrostore are already doing it using a technique known as hydrostatic compensation. Compressed air is stored underground and then water is used to balance pressure and help prevent structural damage to the cavern. Hydrostore reckon their system will be good for around 8 hours of discharge with a roughly 66% round-trip efficiency, which when you add in longevity starts to look reasonably competitive with other long-duration storage technologies. It's still a much lower round-trip efficiency than lithium-ion batteries, of course, though, and performance depends heavily on geology, so large-scale projects are still relatively rare. And critics have pointed out that the thermodynamics are pretty unforgiving. In other words, you can improve the system, but you can't eliminate the fundamental losses entirely. So where does that all leave us then? Well, first of all, there's no question the need for long-duration energy storage is absolutely real. As we add more wind and solar to the grid, we need ways to balance supply and demand over hours, days, and even weeks. Secondly, abandoned mines are a genuinely interesting resource. They're already there. In fact, the Oak Ridge team tell us there are about 500,000 potential sites in the US alone, and there are probably millions more around the world. They're often located near existing infrastructure, and they represent an opportunity to repurpose industrial landscapes and perhaps restore some gainful employment and dignity to decimated local communities. But just like every other technology we've ever looked at here on the Just Have a Think channel, abandoned coal mines are not a silver bullet. They come with geological uncertainty, engineering complexity, site-specific constraints, uncertain economic viability, and perhaps most importantly, a long history of promising ideas that struggle to make the leap to commercial reality. This latest research illustrates quite nicely the fact that the energy transition is not going to be delivered by a single breakthrough technology. It's going to be a messy, complex mix of solutions. Some will succeed, some will quietly disappear, and a few, like this idea of turning old coal mines into giant underground batteries, might just evolve over time into something quite different from what we originally imagined. Now, I know there are some strong opinions for and against this sort of technology, so if you've got experience or knowledge in the field, or if you just feel a burning desire to express yourself on the subject, then as always, the place to leave your thoughts is in the comment section below. That's it for this week though. A big thank you, as always, to the amazing folks who support the channel via Patreon and who help me to keep ads and sponsorship messages out of all my videos. And an extra special thank you to the folks whose names are scrolling up the screen beside me here, all of whom celebrate an anniversary of Patreon support in May. You can join them and get the chance to leave feedback on preview versions of each video and take part in monthly content polls and chat directly with me by visiting patreon.com/justaveathink. Don't forget to like and subscribe if you found this video useful, and most important of all, thanks very much for watching. Have a great week, and remember to just have a think. See you next week.